Alright, so now that we have two different types of velocity, our linear or translational or tangential velocity that we've been talking about all semester, and now we have angular velocity. So now that we have two different types of motion, so forward motion and circular motion, we need to discuss how that changes our kinetic energy. So an object that rotates will have rotational kinetic energy. An object that moves forward, so slides forward, will have translational kinetic energy. And if you're rotating and moving forward at the same time, you'll have both rotational and translational kinetic energy. So we need to be able to calculate rotational kinetic energy because we already know how to deal with translational kinetic energy. Alright, so we're going to start by focusing in on a single particle within an object. So we're going to have a disk that is going to be rolling forward. And I don't know why I draw the center first because I always have to erase it and fix it. So we're going to focus in on a single particle along the edge here. So this particle is going to be moving forward because the system is moving forward. So we're going to have velocity of the center of mass of the system. But at the same time, this particle is going to be moving down this way due to the fact that it is rotating. So we're going to refer to that as V prime. And I'm going to indicate that this is due to a single particle. So the individual velocity of one particular particle is a combination or a vector sum of the velocity of the center of mass of the system, because you're moving forward, plus the V prime, which is the fact that the particle is moving down as it's moving forward. Now mind you, I say down now, but as the object rotates, the direction it points is going to change. Now mind you, this is a vector sum, not literal addition. Alright, so we know kinetic energy equals 1/2 mass times velocity squared. So in this case, so remember, right now we're just dealing with one individual particle. And our velocity equals the vector sum of our two different types of velocity. And since this are vectors, I need to do a dot product rather than actually just squaring them. Alright, so when I do my dot product, and right now I'm just going to FOIL it, and then we are going to focus in on what happens due to the nature of the fact that we're doing a dot product. Alright, so 1/2 mass, and we're going to get VCM squared. So since we're dotting the same variable or the same vector, they'll automatically pair it to each other because it's the same thing. So we've done our dot product there. When we go to do the next term, notice the angle in between the two of them, that it's a 90-degree angle here. So this dot product is just 0. And then we're left with our prime velocity, which is the velocity of the particle itself. And that just becomes squared because we're dotting the vector with itself. And this all needs to be in parentheses here. Alright, and now we're going to sum over all particles, which in essence just turns us into the mass of the object. And V prime squared. And we can do that now because we no longer have vectors in our equation because we took the dot product, which the result of is a scalar. And this here is our normal translational term. And this here is going to be a rotational term. Now notice here that this V prime here is tangent to the object. So we can go back to the idea that V tangential was equal to R omega. So this allows me to then rewrite our second term here as R omega squared. So let me distribute the square. And notice mr squared is typically how we think about moment of inertia. So we can rewrite this second term as 1/2 moment of inertia times our angular velocity squared. So our total kinetic energy term has our 1/2 times moment of inertia times angular velocity squared, and it also has our translational that we had up here, which is 1/2 mass times velocity squared. Alright, so this is now our full kinetic energy term. Now, before we try to use this in a conservation of energy type problem, there's one more thing we need to discuss. So we talked about the idea of we have the velocity of the center of mass of the system. And so for an individual particle, those individual particles are always going to be moving forward. So that's your translational motion. But at the same time, you have rotation of the individual particles, so v prime. So if the velocity prime and the velocity of the center of mass have the same magnitude, then we get a scenario right like this, where this one's pointing in the positive x, this one's pointing in the negative x, and v summed actually equals 0 here. And this is referred to as no slipping. And this is the type of scenario we're going to be working with, because when there's no slipping, we don't have to worry about work non-conservative due to the frictional force, as we saw in an earlier example problem. As soon as you start slipping, you apply a force over a distance, and then you have to worry about work non-conservative. So you need friction to cause the rotation of the object, but at the same time, you don't want to be dealing with friction in terms of the object slipping forward. So how friction gets dealt with when we're dealing with rotational motion is a little different, where it's hidden inside of the torque that's applied, but not dealt with in the conservation of energy, because technically speaking, you're not sliding forward, so you're not applying a force over a distance. And what this assumption also means that we can use this relationship here to replace either this term here, so you replace the velocity there with r times angular velocity squared, or you rearrange it and replace this one to get it in terms of velocity over the radius. So this sort of eliminates the number of variables you actually have to deal with. We're also going to be assuming our surfaces are smooth. If you hit a scenario where something is rolling down an incline, and instead of being smooth, it bunches up, so you'll end up with like sort of a hill of material. As the object actually hits this spot here, you end up with a component of the force normal from this bunched up material that does not go through the center of mass and therefore is not parallel to the lever arm, and so it actually exerts a torque and slows down the rotation of the object. So we're going to, for that reason, be assuming that our surfaces are smooth and aren't going to have material on them that's going to bunch up and cause the force normal to exert a torque on the rotating object.